In today's talk, we're going to talk about counting words or strings. You'll remember that in the earlier examples we had for using generating functions, we were counting combinations or numerical partitions, or even the sums on the faces of two dice. In all of those examples, the order didn't make any difference. Well, now when we're counting words, order will matter. So let's take a look at an example. Let's say we want to count the number of 6-letter words from this set ABC that use at most 3 A's, at most 4 B's, and at most 2 C's. Let's start with a sort of pre-generating function where for the A's we have a factor that looks like 1 plus A squared plus A cubed. Just as before, we're going to let this 1 denote the choice of choosing 0 A's. Here the A will represent 1 A, this will represent 2 A's and 3 A's. Then we can choose either 0 B's, 1 B, 2 B, 3 B's, or 4 B's. And for the C's, either no C's, 1 C, or 2 C's. When we multiply these three terms together and expand, we'll have a bunch of different terms in the expansion, quite a few. Here's some example of terms where the total power is 6. That will represent a total of 6 letters. Here's one of those terms. One term will be an A times the B squared times this. Well, there's actually a bad example because we can't use that. I apologize. Let's look at the next example. We have an A squared, B squared, C squared. We can use 2 A's, 2 B's, and 2 C's. Well, a word with 2 A's, 2 B's, and 2 C's would be something like AA, BB, CC. But there are many, many other choices. There are all the different rearrangements of this. It could be AB, AB, CC, and a huge number of different rearrangements. How many words would correspond to this one term which says we have 2 A's, 2 B's, and 2 C's? Well, the number of rearrangements is easily seen to be 6 factorial. We've certainly discussed this problem in the past, over 2 factorial, 2 factorial, 2 factorial. What about the term that looks like A, B to the 4th C? That would mean a word that has 1 A, 4 B's, and 1 C, like A, B, 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 C. Of course, there are many rearrangements of this word that would also have 1 A, 4 B's, and 1 C. A rearrangement might look like B, B, C, A, B, B. And of course, a huge number of other ones. How many total? There would be 6 factorial over 1 factorial, 4 factorial, 1 factorial, which is just 6 factorial over 4 factorial, or 6 times 5, which is 30. So there are 30 words of this form. Here we'd have 6 factorial, which is 720 divided by 8. That's just 90 words of this form. One more quick example, because I made a mistake typing in the first one. What if we have a term that looks like A cubed, say B squared, C? Well, we'll have a total of 6 factorial over 3 factorial, 2 factorial, 1 factorial words that use 3 A's, 2 B's, and 1 C. They would all be rearrangements of AAA, BB, C. There are this many rearrangements. That's the same as 6 factorial over 6 times 4. That would be like, 720 divided by 6 times 2, which is 12. There would be 60 words of this form. How can we somehow create a system, a generating function, that would take into account that we have this many repetitions, 6 factorial over 2 factorial, 2 factorial, 2 factorial, not repetitions, but this many different words that all should be accounted for by a term of this form. And we have a different number of words that would correspond to a term of this form. Notice in all 3 of these cases, the total power is 6. These are all 6-letter words we're looking at, but we have to count each one a different number of times. Well, The important thing to notice is these denominators, 2 factorial, 2 factorial, 2 factorial, correspond to the factorials of the exponents in the a, b, and c. The same thing here and the same thing here. We can build that into the generating function by putting them in here. Change this a to an a over 1 factorial, which doesn't really change anything. Change the a squared to a squared over 2 factorial, the a cubed to a cubed over 3 factorial. Then when you use an a squared, that's like picking this term. I'm sorry, when you use two a's, that would be like picking this term, and you'll have that 1 over 2 factorial built in. When you use an a cubed, you'll have this 1 over 3 factorial built in from the choice of this term. That takes care of the denominators, but we still have the 6 factorial in the numerators to deal with. So we're going to want to take care of the denominators just the way we saw before. But now we'll be off by this factor of 6 factorial. So what do? We put that in the end, and we say we just look for the total, look for a term where the total power is 6, or look for all the terms, I should say, where the total power is 6. We'll get this one, this one, this one, and they'll have the correct denominators, which will add up, and we just multiply the answer by 6 factorial at the end. How can we formalize this? Well, we're going to create a generating function in our one variable x by creating one factor that looks like this. This will correspond to the a's. This factor here will correspond to the b's, the choice of 0, 1, 2, 3, or 4 b's. This one will correspond to the c's. We'll then expand all this, and there'll be some term that looks like x to the 6th. That will be all kind of a compilation, adding up all the terms where the power from the A selection, the power from the B selection, and the power from the C selection add up to 6. You're going to have the denominators that appropriately take into consideration how many repetitions we have. The only thing we're missing is the 6 factorial. So what do? The number of 6-letter words will be 6 factorial times the coefficient on x to the 6th. And we're going to see in a minute that's the same as saying we write this out as something divided by 6 factorial, and then we just want whatever coefficient here is multiplying x to the 6th over 6 factorial. That coefficient would just itself be 6 factorial times whatever would have been multiplying x to the 6th if we didn't have this denominator here. So here's the way this works out, and I use my computer to compute this. We have our generating function. That's all of this. I expanded it, in this case using the computer, and we got a 9th degree polynomial. And we look at the coefficient of x to the 6th, which is 41 over 72. And then we just multiply that by 6 factorial, which is 720. And so the answer is 720 times 41 over 772, which is exactly 410. Notice that these coefficients are not integers, they're strange rational numbers, but we know ahead of time that once we multiply the correct coefficient, in this case the coefficient on x to the 6th by 6 factorial, what we get will definitely be an integer because it will count something. So we shouldn't be surprised that 6 factorial times this rational number, 41 over 72, is an integer. It's 410, and that answers the question. Let's look at now a much simpler example. How many words are there of length 3 from the alphabet with just 2 letters, A and B, if we have to use at least one A? Well, we can construct an exponential generating function for the answer. So we're going to call these things exponential generating functions, and we'll see in a minute why we use that name. For the A's, we have to use at least one, so there's not going to be a term 1 here, which represents 0 A's. It'll be either 1A, 2A, or 3 A's. And since we have to use at least one A, and the total length is 3, we're going to use either 0 B's, that's for the A's here. We're either going to use 0 B's, 1 B, or 2 B's. We can't use 3 B's because we need at least one A. Now we want to expand this. Well, I'll show you. We can still use synthetic multiplication, and I still want you guys to be comfortable with this. How would we multiply these with synthetic multiplication? Well, the second factor is just represented in synthetic multiplication by 1, 1, 1/2. It's okay if there's not an integer there. This first factor would correspond to 0. Don't forget the 0 in the constant place. 1, 1/2, 1/6. And now we want to multiply those together. Well, the upper factor times 0 would just give me 0. I could write a row of zeros, but there's no reason to do that. Then we shift over 1 and take this 1, 1, 1/2 times a 1. 1, 1, 1/2. It's shifted over 1 because it's being multiplied by this 1 here. Then we shift over again and multiply by 1/2. So I'll have a half, and then 1/4. And then we shift over again and multiply by a 1/6. So I'll have 1/6, 1/6, and a half times a 1/6, which is 1/12. And what do we get? Well, let me still leave that 0 there. We're going to start with a 0, then we'll have a 1, then we'll have 3/2, then we'll have a half plus a half plus a 1/6. That's 7/6. That's 1 plus a 6 is 7/6. A 4th plus a 6th. If you put that all in twelfths, that would be 4/12 plus, 3/12 plus 2/12, which is 5/12. And finally, of course, it's just 1/12. And when we write that, we'll see that that's exactly what I've written down here. That's our exponential generating function for this problem. I'm going to rewrite that, and there's no reason you have to do this, but it's sometimes nice to rewrite that, not in terms of powers of x, but in terms of powers of x over the corresponding factorial, x over 1 factorial times 1. Here we have 3/2 x squared, which we can write if we want as 3 times x squared over 2 factorial. That's just the same as this second term. 7x cubed over 6. 6 is already 3 factorial, so that's just 7 times x cubed over 3 factorial. 5/12 x to the 4th. If I multiply by 24, which is 4 factorial, I get 10 times, that should be x to the 4th over 4 factorial. That was a typo there, so we'll fix it. Then this one is 120 times the 12th, which is 10 times x to the 5th over 5 factorial. And what is the answer to the question? We want words of length 3. So what we want is the coefficient on x cubed over 3 factorial. So that coefficient is 7. Again, we could have written that as we want to find 3 factorial times the coefficient on x cubed, or as we did here, we just want the coefficient on x to the cubed over 3 factorial. Either way is fine, and the answer is 7. Now, is this a question we could have answered easily without generating functions at all? Of course it is. We want words of length 3 from a 2-letter alphabet. If there's at least one A, well, how many words of length 3 are there just using A and B if we had no conditions? Well, there would be 2 cubed, or 8. How many don't have at least one A? The answer is 1, the word BB. And so the answer is 7. So this is certainly the correct answer. And we've solved the problem. I want to now generalize things a little bit and talk about an infinite generating function of this form and ask how many words are there of length n from the alphabet A, B. Here we'll have no conditions to start out with. Well, the generating function for this problem is just, again, what we call an exponential generating function, 1 plus x over 1 factorial plus x squared over 2 factorial plus x cubed over 3 factorial, etc. We'd have a factor like that for the A, we'd have another factor like that for the B, so we're going to take this whole thing and square it, this power series. The answer we want is the coefficient of x to the n over n factorial in this resulting expansion. And here's why we call these exponential generating functions. This series is exactly the power series for the function e to the x, the exponential function. So this generating function for the problem, how many words are there of length n from this 2-letter alphabet, is just the generating function, which is e to the x, all quantities squared, which is the same as e to the 2x. And how do we write down e to the 2x? We just plug in 2x in place of x in the series for e to the x. and we get 1 plus 2x over 1 factorial plus 2x squared over 2 factorial, etc. But that can just be written as a sum from n equals 0 to infinity of 2 to the n. We just factor that 2x squared is 2 squared x squared. Here we have 2 cubed x cubed, etc. So we have 2 to the n x to the n over n factorial. The answer to the question is the coefficient of x to the n over n factorial, which is exactly 2 to the n. So what have we learned? Well, the answer is we've learned nothing new in the answer to this question that we didn't know in week 1 of the course, which is that there are precisely 2 to the n words of length n from a 2-letter alphabet. But this is the exponential generating function approach to something we learned in week 1. Now you might think, okay, that's ridiculous. That's so much more complicated than just using the product rule to get the answer 2 to the n. And of course, that's correct. But using a generating function now, we can alter it if we have other conditions that we want to deal with. As far as those other conditions, the last 3 exercises, the last 3 or 4 exercises that I assigned you, the last ones that are in this section G of the book, will show you how we can incorporate other conditions. So I'll leave that to you guys in the exercises.